thing. So afternoon all, we have capacitance. We're going to start the capacitance handout properly today. Well, hopefully we finish it. We're going to run a little overtime. I want to finish around 3 because we do have to make up for the last day. All right, so capacitance, we had started capacitance last day. All right, and just reading through capacitance is basically the ability of a device to store electricity. That's what it is. It's defined as the charge required to cause unit change in the potential of a conductor. Unit being 1 volt and 1 coulomb to give you 1 farad. So the formula for capacitance, C is equal to Q over V. And you're going to get 1 farad, the unit of capacitance is the farad, is equal to 1 coulomb over 1 volt. Please note that 1 farad is an extremely large quantity because coulombs are also a really large quantity. We don't use big numbers of coulombs of 1 and 2 and 3 coulombs. All right, we use smaller values. And similarly for capacitance, we use smaller values usually in the range of micro and nano. Remember, micro is 10 to the minus 6 and nano is 10 to the minus 9. And we had gone through here the other day. We had started it, but just to look, isolated conducting sphere, you all have to know how to work out the capacitance for 2 situations. 1 being the isolated conducting sphere, and 2 being your parallel plate capacitor. Now, the parallel plate capacitor is what we use almost all the time. So, just to remember the equation here, capacitance is equal to Q over V. So, if we know that V is equal, we just did it in charges, is equal to Q over 4 pi epsilon. A, in this case here, A will be your radius. It's the same thing, right? If you have R and A, it's the same thing. And we're going to take this V and substitute it into the equation of C is equal to QV. So you're going to get Q divided by this whole term. All right, so it's going to be Q. Let's get some writing space. So it's going to be Q over 4 pi epsilon A. And remember, when you divide by a fraction, it goes up on top. So you're going to end up with 4 pi epsilon A. So that's the capacitance of a isolated conducting sphere, meaning a sphere that is just probably attached to, a conductor, right? So how do you work out your capacitance? It's going to be 4 by pi by epsilon, which is the permittivity of a material. We're not looking at the permittivity of free space. The last day, remember we said this, in charges we looked at epsilon naught, which is the permittivity of free space because we looked at the action within a vacuum or in space. But capacitors need a material to work. So we're going to look at permittivity of a given material. We're going to look at what kind of material that is soon. So please note it's not 4 pi epsilon naught, it's 4 pi epsilon by A being your radius of your sphere. Okay, moving on, parallel plate capacitor. This is the one that we use almost all the time. All our capacitors, even the capacitors we use in school, are parallel plate capacitors. So simply looking at the diagram, what we do, we have 2 conducting plates, that's the gray plates here. And then we have a material in the middle called a dielectric. We're going to look at dielectrics right after we do the maths. So let's do the proof for the capacitance of a parallel plate capacitor. Now this one does come for exam. I have seen this proof come in exams. So let's consider a capacitor with plates of common area A. So our plate has an area of A. separated by a medium of thickness D. So if that is our plate, first plate, second plate, connected to your circuit, it has some medium in between. So the distance between these plates, because it's two flat plates, it's going to be a consistent distance. It's going to be a constant distance. So this distance between your plates is D. And having a permittivity, being the material between your plates, it has a permittivity of epsilon. So let's read again. If the plates have charges of plus Q and minus Q, because if it's in a circuit, you're going to have the side that is connected to the positive side of your battery and the negative side of your battery. So you will have an area that has more charge, more positive charge than the other one. Remember, we said in this topic, in circuits particularly, charges, plus and minus charge, are a result of too many electrons or too little electrons. All right, or more electrons on one side and less electrons on the other side. We're not talking about protons in circuits. And we have reached circuit section again. All right, so please note capacitors must have a correct polarity. This is the one device that you need correct polarity for. You must hook up the positive to the positive. You must hook up the negative to the negative because the plates are labeled in a certain direction. And this is the one device, if you hook it up incorrectly, it might pop and blow on your board, as in it's going to die right in front of you with some little white smoke. So please remember, capacitors are very important when it comes to polarity, hence why we must have a positive plate and a negative plate. So reading again, and the charge density of common sigma. All right, common sigma is your charge density. All right, and here we give charge density as Q over A, where Q is equal to your charge and A is equal to your area. Why don't we use volume instead? Because the volume is area by thickness or height, and we're going to find that in here just now. So we have a new term to learn here. We have sigma, common sigma. Sigma is your charge density or charge over area. So there's an easy way of working this out. There is E, your electric field, is given by, this is a new formula for you all to learn, sigma over epsilon, or QA over epsilon. So this is something new to use. All right, electric field in a capacitor is given by Q over A epsilon. And we are going to recall the equation of E is equal to V over D. Remember, we just did this last week. We're going to substitute this term for E. So let's look at here. We're going to end up with VD is equal to Q upon A epsilon. What we're going to do, we're going to bring our charge and voltage on one side. Why we bring our charge and voltage on one side? If you know, we just did it. C is equal to, let's go up and check again. C is equal to Q over V. So what we do, we carry the V. If you want to do this maths a little, take our time and do it. V over D is equal to Q over A epsilon. We cross multiply everybody, so we're going to get QD is equal to VA epsilon. I carry my V on this side, I carry my D back on the other side. I think there's something wrong with this equation. All right? So you're going to get Q over V is equal to A epsilon over D. Why did I do this? Y'all, this one is wrong. Let's ignore that. All right, this is, I knew I was supposed to take this out of the handout. So if Q over V is equal to A epsilon, A by epsilon over D. We know that capacitance is charge over V. So we're just going to have, how do we find the capacitance of a parallel plate capacitor? All we do, we find the area of your plate, multiplied by the permittivity of the material between the plates, multiplied by the distance between your plates. So it not multiplied, divided by your distance between your plates. So this is a very easy equation to remember. All you have to do to go from one equation to the next, if you want the steps in doing this, let's look at the steps easy. One, in doing the proof, that is, E is equal to Q over A epsilon, sorry. I know E is equal to V over D. So I'm going to end up with V over D is equal to Q over A epsilon, and then you just find A Q over V term, or your capacitance term from there. So dielectrics. Now, without a dielectric, a capacitor will not work. It will work for like a trillionth of a second, which is not any sort of appreciable time. So what is a dielectric? Let's read. Capacitors are basically two sheets of metal with a material in between them. That's the very basis of a capacitor. You can make a capacitor out of metal and paper. The material is called a dielectric. The molecules of a dielectric, let me just make this larger so you all can read it easier. Right, the molecules of a dielectric between the plates of a charged capacitor are in an electric field. The positive nuclei are urged in the direction of the field because remember, positive charges will get attracted to your electric field and negative charges will be repelled by your electric field, and a negative electron in the opposite direction. As a result, the molecule becomes distorted or polarized by the field. Electric dipoles are thereby formed. So what we have here, if you were to look at our diagram larger, if I have my regular molecule, let's all assume our molecule is nice and symmetrical and spherical in shape. I have a very evenly shaped, regularly shaped molecule, no electric field applied to it. But the instant I apply an electric field, it causes the molecule to distort or to get stretched, where I'm going to have the positive side wanting to go in the same direction as the electric field, and the opposite is happening with your negative side. So what it does, it basically distorts or causes your charges to get not so evenly distributed in your molecule. And the molecule doesn't break apart. All it does, it goes from regularly shaped to distorted to give us a sort of positive and a sort of negative pole. Hence why, of all the devices you all will use, polarity is extremely important in this topic. So continue reading. The positive potential of the positive plate is reduced by the negative charge at one surface, and the negative plate is made less negative by the positive charge on the other side of the dielectric. Or the diagram is going to show that. The PD between the plates is therefore less than it would otherwise be. More charge is required before the PD between the plates is equal to the applied PD, and thus capacitance is increased. So what did that just say? If I have my circuit connected to my capacitor, this is our positive plate, this is our negative plate, right? We assume that current flows into your capacitor. So we now have our positive plate. You hook up your positive side of your capacitor to the positive side of your battery. And since this becomes the positive side, right? If I have a positive side on my capacitor, my electrons are going to get attracted towards my positive plate in my capacitor. Wouldn't that make sense? Basic electrostatic application. If this is my plate, these are my plates, and this is my wire going in and out. If I have a positive pole, a positive section on my capacitor, my electrons or my negative charges or my negative sides of my molecules will want to be attracted towards my positive pole. So suppose these are your little distorted molecules with negative and positive poles in them. Just think, it's just a little distorted molecule that looks like it has a negative and positive pole. So you're going to end up with the negative sections facing one side, and then you're going to end up with the positive sections facing the other. So if I end up with all the positive poles in my dielectric facing one side, then these positive sides will also be attracted to your negative. Now we are going to look at some very basic maths here. Very basic maths and how the dielectric reduces your PD between your plates. Remember, your PD is your potential difference. So suppose I have 0 volts on one side and 12 volts on your next side. As before I put on my battery, as I put on my battery, put on my circuit, my power supply has a potential of 12 volts. My negative pole has no voltage. So what it does, your PD flows across your circuit. Now, when it hits the capacitor, all these positive and negatives are going to cancel out each other. So suppose I have, let's just take out all of these here to add it up. And now we're just going to do some arbitrary numbers right now. This is not what actually happens. So if I have 12 volts on the outside and I end up with a whole bunch of plus and negative charges affecting each other, plus and a minus is going to give you 0. So that means you're going to end up probably with a charge inside of your, or a potential difference inside of your capacitor is less than outside of your capacitor. Why? Because these plus and negative charges, because they are influencing each other, they are reducing the potential difference between your plates. So outside of your capacitor, we have a voltage of 12 volts, but inside of your capacitor, we have a smaller voltage. So what happens, because of the smaller voltage inside of your plates, it takes a little more time for your charge to build up. Y'all, that made sense? You digesting, okay. Continue reading, certain molecules are called polar molecules. Certain molecules called polar molecules are polarized even in the absence of electric fields, and consequently, they increase their capacitance. So almost any material, yeah, digest. I know it's a brand new topic. You're gonna have to read it and go through it. Let me just move you from here. All right. Certain molecules called polar molecules are polarized even in the absence of electric fields. So a normal atom will be your nice cylindrical atom with your negative charges on the outside. A polarized atom is an atom, not atom, an atom or molecule that sort of pulls your negative side to one section, and because you're pulling the negative side on one section, the positive sort of remains on the other side. So you get a polarized molecule. Now this happens when we apply an electric field. Now, some materials are like this by themselves. You can actually cause some materials to be polarized, or in their natural state, they are polarized. This doesn't sound really familiar or really similar to the next topic we're going to be doing. Anybody? What does it sound really similar to? that we are going to be doing? Hint, hint. Anybody? Let's look at this. We have our material here that are not polarized, and the instant we apply a field to it, we cause it to become polarized. If we remove that field, they become unpolarized, but there are some materials that naturally exist as polarized. Isn't there something that we're going to be doing, a topic that we're going to be doing that works exactly like this? Anybody? Starts with M. Nobody? All your mics working? I lost my pen. Oh. This is almost exactly like magnetism.
Miss, I know that you know. I know that you know. But I was going to electromagnetism, but I was like, I wonder if that wrong.
Well,
And then,
the electromagnetism is actually this part here, where you could
well, that
take
was
a
saying because
material.
that remind me. Yes, that remind me how we did do that in Form 5, but I still have hush my mouth because, you know.
And I said it's a topic we are going to be doing. What is right after electricity in this topic? Not magnetism. The very next part. Jabari, you're terrible. Right? This is almost exactly like magnetism because the nature and how this behaves, this is how we get magnets. We take a molecule and we distort the molecule so that we get a positive and a negative pole or a north and south pole. And we can get materials that actually have these dipoles that exist in nature, and that's how we get a magnet. It's basically the same exact physics. But here we are looking at any material. We're not looking at a magnetic material. We're looking at a material where we can actually influence the dielectric with with an electromagnetic field or electric field, or we have some materials that are naturally by themselves polarized. So here, let's just look. We have some unpolarized materials. So that means, you have the plus and negative side in any direction whatsoever. There's no alignment of anything. Doesn't this look exactly like how magnets are? And the instant we introduce a magnetic field, we cause all of them to line up in the same direction. And by doing this, we are going to create a negative pole inside of your capacitor and a positive pole inside of your capacitor. All right, now the few lines I have here, I did tell you all you should be printing your handout to put in some extra notes. I want you to list for me um, 5 common dielectrics. And if you want, you could go even further. Dielectrics that exist without any electric field and dielectrics that they use with an electric field. So you're gonna have to write it down because that does come in exams. And I left this out. You all go and give it a read up. Type of capacitors. Even though I give all your homework and I just answered it myself, but that's okay. There are many types of capacitors. The intended use must take factors such as heat, magnitude of charge in PD, frequency of the alternating current passing through it. Not the alternating, the DC current passing through it. Wax, paper, plastic, ceramic, and mica can be used as dielectrics, but the capacitance of these very rarely exceed a few microfarads. So Common capacitors like what you all will be using, not even what you'll use in school, because the ones that we use in school are usually 3000 microfarads and 4700 microfarads. These are the capacitors we have in school. So we don't have the tiny, tiny ones. I've never seen a small, really small capacitor. We have okay size ones. So wax, paper, plastic, ceramics, these make very small capacitors. Capacitors like what you probably need in your phone or your calculator. And if you've never seen a capacitor before, you're going to see what they look like now, and then you're going to think back. You have seen a capacitor sometime in your life. Electrolytic, electrolytic capacitors have high capacitance values, and this is nearly a zero point 0.1 farad, and they offer greater stability at high voltages being a few hundred volts. Now, whenever you all use a capacitor, you are going to notice when you have a capacitor, they're going to tell you what the capacitance is of your capacitor. This is a diagram. This is one of the capacitors, what we have in school. Your capacitors will always tell you what is your capacitance, and then they will tell you what is the maximum voltage your capacitor can work at, because you can only build up so much PD between your plates. It depends on the makeup of your capacitor. If your capacitor has a very small or very um, low capacitance dielectric, then it will not be able to store a lot of current. The capacitors we have in school usually work at 12 and 24 volts, but we will never ever use a power supply more than 9 volts in school. All right, so please be careful whenever you all are using the capacitors. They, they do list two values on the capacitors, usually your capacitance and the working voltage of your capacitor, or the working PD of your capacitor, because it can only hold so much. So polarized capacitors, what I do suggest you all do, I did it on purpose, read up what is a polarized capacitor. This is like 2 lines of reading, if so much. All right, so read up what they mean by a polarized capacitor. And in polarized capacitors, one lead is marked as positive and the other is negative. Actually, most times they only mark the positive pole because, no, the negative pole, because if you know the negative, you obviously know the positive. So your symbol for a capacitor, it can look like either of these, but in practice, we just have it here as basically like a battery, except with equal length sides. And anytime you all are using a capacitor, you must indicate which side is your positive and which side is your negative of your capacitor. Where'd my white pen go? All right. All right, so remember always, always, always to hook up your capacitor correctly. The positive pole of your capacitor must connect to the positive pole of your battery. The negative pole of your capacitor must connect to the negative pole of your battery. Always be very careful when you're doing these things. And it's really nice what they do. We have radial capacitor. Those are the ones that look like a little cylinder. And let me see if I can draw this better. And on your cylinder, it's usually covered, our ones are covered in dark blue. Right, they're covered in dark blue plastic wrappers. So the outside will be nice, this dark, dark blue. And they will just have where your negative side is, they will have a nice silver area. This is a horrible drawing, y'all, but whatever. All right. Wherever your negative pole is actually a silver strip, and they will come and write negative on it. So it's really hard to get the polarity wrong in this. They actually do have one side labeled as your negative pole. So you're going to have one wire coming out here and one wire coming out the next side. All right, so please note, always look for your polarity. And it's even better than a battery. A battery tells you where the positive side is. All right, here they list the entire strip, the entire side of your capacitor tells you where your negative side is. So just be mindful, please, 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 of the type of connections you all make with your capacitor. Okay, so let's go back and read basic types of polarized capacitors. We have electrolytic, we have tantalum, and can capacitors. I have no idea what these are. I have never seen them in my life. I should probably look it up and see what they look like. Never seen them, ever. Types of electrolytic capacitors, which is what we use in school. They are radial. Radial are the ones that look like little cylinders, and then they have axial ones that look like a little kind of, I don't know even how to explain it, like a little cone. Next time you all happen to see the circuit board of probably your an old TV or even your calculator, if you want, you can take apart your calculator. And if you look on the circuit board, you're going to see where you have capacitors. Capacitors will look something like this or like this. And they usually label it with a C. Your resistors are usually like your small little resistors, your carbon resistors, which your lines are called, and they label it R. But your capacitors in your, say, your phone or your calculator will look like one of these. So next time you happen to take apart your stuff or you happen to see a circuit board, take a look at them. Right? If we were in class, I would have actually opened my calculator and show you all. All right, but give it a try and see if you want to, if you care to go and try. So we use radial capacitors in school. Let's trying to get back our stuff. Right. Capacitors in circuits. The maths here is going to be, let me just make sure I did not lose my diagram. I did lose my diagram. I'll get back. Capacitors in circuits. Now here we're going to remember our Kirchhoff laws. Right? In our Kirchhoff laws, we know that first one, I is equal to I1 plus I2 plus I3. We know that for a parallel circuit. And we know that V is equal to V1 plus V2 plus V3 for a series. We're just going to remember that for right now. Let's label our diagram because you all are going to do the proof for the series circuit. I'm not doing the series circuit proof. So I have a voltage here. My voltage of my power supply is V. And since this is a parallel circuit, your voltage across each branch is the same. I will have capacitance 1, capacitance 2, capacitance 3. And since this is a parallel circuit, I know if I have current coming into my branches, I will have I1, I2, and I3. And we do know that charge is equal to current by time. So if my charge in each branch is different, now if my current in each branch is different, then also the charge in each branch will be different. So that means that Q1, Q2, and Q3, and the charge delivered by my power supply will be Q. So let's look at that. If I have my total charge will have broken up into different branches, right? So I1 is equal, I is equal to I1 plus I2 plus I3. We are going to use this relationship of I and Q are basically related to each other. It's the same thing. If you have your circuit, your current breaks up into different branches. So then your charge will also break up into different branches. So we're going to use our formula of um, using our formula of C is equal to Q over V. We can get Q is equal to CV. So let's look at this. Q will be equal to CV, which is equal to C1V plus C2V plus C3V. Our V is a constant. Why is it constant? Because we are in a parallel circuit, so our voltages are the same across each branch. So we can cancel that out and we can get our total capacitance is just the sum of your capacitors in a parallel circuit. Notice this is the exact opposite of your resistors. When we had done resistors, our total resistance was 1 over R1 plus 1 over R2 plus 1 over R3 to the minus 1. Here it's the opposite, the complete opposite. So let's just go through that really quickly. I know it wasn't a hard proof because we've done this before. Using Kirchhoff laws, your current is different in each section. And current is related to charge by the equation of Q is equal to IT. So instead of the I, we're going to replace it with the Q because the time will be the same. So you're going to end up, instead of I, we'll have Q. Instead of I1, we have Q1. I2 gives us Q2. I3 gives us Q3. Using the equation of capacitance is equal to charge over voltage, we can get an equation or get a relationship for just charge, and charge will be capacitance by voltage. So let's replace everybody, right, with their CV equivalents. So your total charge, which is Q, your total charge, would be a total capacitance by your voltage. Q1 will be C1 by V, Q2 is C2 by V, and Q3 is C3 by V. Since V is the same, we just cancel them out and we get our total capacitance is just the sum of our capacitors, and this is only for capacitors in parallel. It's the opposite of resistors. So yeah, that's the thing here. So let's see if we can work out. Now I do have some space here for a reason. Let's see if I can get this out of the way. So imagine that we have a circuit. I don't even know where the circuit disappeared to, but we can draw our circuit. Look, I'm just going to draw it. It's a terrible, terrible circuit. Don't worry. It does the job. So I have a series circuit with three capacitors in series with each other. And I want to work out what is the capacitance of my three capacitors in series. Now the math says basically the same thing like before, right? We know that the voltage across a series circuit varies. So we know V is equal to V1 plus V2 plus V3. And the charge through my circuit is going to be constant because charge is the number of electrons flowing through your circuit. So charge is the same going through. So using C is equal to Q over V, let us find a relationship for V. What will be V equal? What will V be equal to, you all, from this? Anybody? Anyone? If C is equal to Q over V, what is V?
Message if C is equal to Q over
If C is equal
V
to,
will be C by Q,
eh?
won't it? Hold on, huh?
No. No.
Hold on.
V. You add up first multiply.
Q
Anybody
over
else?
C? Q over
Q
C.
over C.
Yes,
Oh
yes,
my
that's true.
goodness.
Sorry, miss. That was just like a quick, but I didn't think now, but now I think, right?
That's a Friday afternoon.
Yeah.
All right. Q over C. Good. All right. So what you're gonna do, you're going to replace your Q over C's for each one of these. So instead of writing V, you're going to do Q over C for each one and tell me what you all get for the formula. You all are working this out for me right now. Tell me what is the formula to work out your total capacitance for capacitors in series. Pausing the video right now while we do that. It should take us no more than 3 minutes, 4 minutes to do that. So we want to look at how to find the total capacitance using V is equal to Q over V. All right, so I have V is equal to V1 plus V2 plus V3. Now, all if I finish and say, Miss, there's what I get. I don't hear all that, you know. Let's replace every V with Q over C. So Q over your total capacitance will be Q over C1 plus Q over C2 plus Q over C3. Now, Q here is the same. So that means they will cancel out each other very nicely. All the Q's will cancel, thus giving us 1 over Ct is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And if I want to find my total capacitance, it's going to be the inverse of all the capacitance added, and then you do to the minus 1. Remember, I just told you all is the exact reverse of resistors. So your total capacitance of capacitors in series is exactly how we add up resistance in parallel. All right. You all see that? You can see how you could get there from the last line. Jabari, everybody else? I
Yeah, man,
see.
that's it. Um,
Yes.
so just like how you inverse one over CP, right, to make it CP, why doesn't inverse everything and it's C1 plus C2 plus C3?
You did not just ask me that. That's how we add fractions. So tell me. If I had 4 plus 5 plus 6, is that the same thing as tell me 1 over 4 plus 1 over 5 plus 1 over 6 all to the minus 1? Is that the same thing?
Well, no.
No, because how do you add fractions, young man?
You find the is the
LCM. Then your denominator goes into your LCM, and your factor you multiply by your numerator. So you kind of shocked me there. That's Friday
yeah,
fatigue.
my brain didn't do and but then went through that kind of thought process. My bad.
Consider we did this for resistors. You cannot go and just invert your numbers to add them. When you are adding fractions, the formula is different. The method is different. So yeah, that was your one pass for a complete derp moment there, right? Yeah, that was, yeah, dude, that was a derp moment. So your total capacitance for capacitors in series is the sum of your fractions, and you invert your total. So as I said, the easy thing to remember, the resistor, your total resistance, is the complete opposite formula to your capacitors. right? So whatever was your series sum in resistors, it will be your parallel sum in your capacitors. Why did I write a T? And the other way around. All right, so there's a few ways to remember it. Just remember one is the opposite of the next, and you'll be able to work it out. All right, let's see if we can wrap this up. We can actually wrap up nearly the whole handout today. Let's just read this out. When charging, just now, when charging a capacitor, the addition of electrons to the negative plate involves doing work against the repulsive forces of the electrons that are already there. So let's think about this. In a capacitor, right, we have a material that is already charged. All right, this is our capacitor. We have a positive plate, we have a negative plate. And in that capacitor, we already have negative charges in them. So suppose I now come and I want to put negative charges, I want to run electrons inside of my capacitor. My capacitor is going to meet initially some resistance. Now, once I have the electric field running through there, it's going to cause all my molecules to polarize and to get with the, to get with the party, and everybody is going to get nice and polarized, and it's going to allow for easier action of current flow. But initially, when my electrons now reach my capacitor, it's going to reach electrons that are already there. It's going to reach excess negative charge that is already there because we have polarized molecules. Remember, polarized molecules, suppose all the negative sides are sitting towards the area where your electrons are coming in. It's initially going to want to push it back. It's the electric field that takes all the wayward dipoles or polarized materials and forces them to all get lined up in the right direction. So let's read this again. When charging a capacitor, the addition of electrons to the negative plate involves doing work against the repulsive forces of the electrons that are already there. Equally, the removal of electrons from the positive plate requires work to overcome attractive forces. Now, think about it here. I now have, we just did this. We just saw the diagram where we end up with, if you're coming in here, you're going to end up causing a positive plate, and this positive plate, and you have a negative plate. And inside this positive plate is attracting the negatively polarized molecules, and the negative plate here is attracting the positively charged molecules. These molecules are now attracted to the plate. So do you think here, at my negative plate, will I be able to pull out extra electrons? No, these electrons already want to get attracted or are electrostatically attracted to the positive plate that has formed inside of my capacitor. So to remove the electrons from this plate is initially hard to do. Right? To remove them will take a little bit of energy because one, to go in, they don't want to go into the capacitor because they're meeting resistance. And by the time they've gone into the capacitor, they've all made friends and now they don't want to leave. That happens in life. We don't want to go somewhere, then we end up liking it and loving it, and then we don't want to go. Just like life. All right, so the work done is stored in the form of electrical potential energy. And we do know that voltage is a form of electrical energy. And we can work out how much energy is stored inside of our capacitor really simply. I'm not going to go through the maths. Math students and add math students, you all can go through it, but we're just going to learn the formula, all right, of work or the energy to charge a capacitor is Q squared over 2C. or there's a simpler version. First equation to learn, work is equal to Q over V over 2. Why do we have 2? Because we are taking the average of Q1 to Q2, right? If your charge on one plate is 0 and your charge on your next plate is Q, your average charge will be the sum of your two charges divided by 2. So this is why there's a 2 in here. We took the average of your charge, your average charge, where one charge is 0 and the other charge is whatever Q, your maximum charge that builds up, right? We find the average of the 2. So that's why there's a 2 inside of here. The rest of it, it's a maths problem, but you just learn it. Work is equal to Q over V. And then you're just going to use your equation of C is equal to Q over V and substitute it into here. All right, we can even play with this again. We can get Q is equal to CV. So if Q is equal to CV, this equation 1 becomes work is equal to QV upon 2. We know Q is equal to CV, so you're going to write CV by V over 2. So you're going to get CV squared over 2. So that's how you get your second equation. That's equation 2. Let's just write this down properly. So you'll learn how to do this variance with all the equations that you have. So equation 1, your base equation is work, or the energy stored in the capacitor, is charge by voltage over 2. To get my second equation, we use Q is equal to CV, and we substitute it into 1 to give us work is equal to QV over 2, which gives us CV by V over 2, and we get CV squared over 2. So that's our second equation. If you want to get our third variant of this equation, we have work is equal to Q over V. And now we want to get a relationship with V. We use V is equal to Q over C. So we substitute this in here. So we're going to get work is equal to Q V over 2, which is equal to Q by Q over C. And we're going to end up with Q squared over 2C. If you all want to write it down, go ahead and write it down, or you take your screenshot as we said last day. So that's how you get your 3 variants of this question, the 2 other variants of this question. You just have to take one equation and substitute it into the next. So we have 1, we have 2, we have 3. When you learn how to transform from one equation to the next, you don't always need to have all the 3 values. You could just, transpose your stuff. And so let's just get all of these. Give me back my orange pen. You're writing it down, or you took a screenshot?
I take a screenshot.
Me too, miss.
Yes, no, I'll never write again. Okay, and anybody else before I go on? Can I go on? All right, okay.
Yeah, I think you can go on.
Okay, the last part here is pretty long. So we're going to do this the next day. So we've stopped at charging and discharging your capacitor. If it's anything, I can just record how to do the rest because you're not really asking questions. All right, so we'll wrap up there for today. All right, everyone, so that's it for this one.